test the measurement to the real test, and precision is when the repeated measurement give the same results. This is our study. It's actually the first study looking at multiple trophic ectoderm biopsy and also inner cell mass using NGS. As you can see here, we actually show that 35% of the biopsies gave different results, actually mosaicism. And what scared us is this embryo, that the inner cell mass was inconclusive, while in the biopsy, two of them showed normal embryos. So if you take a biopsy from this side, you receive a result of normal embryo. You're transferring actually an abnormal embryo in the inner cell mass. This paper traveled a lot between the journals, and the reviewers actually, their problem was the high number of mosaicism using NGS. They believed that it should be 1 or 2%. This is why it was rejected for several studies until it was accepted in gynecology and embryology. And then soon after it, several other studies appeared in the literature. This is a study from Canada, I believe, no, from the USA. 37 blastocysts were in the first biopsy. They demonstrate an abnormal result, aneuploid embryo, mosaic embryo. Instead of discarding this embryo, they tore them, took another biopsy, and sent them to another laboratory. And as you can see here, of these 37 biopsies that were a priori abnormal, 33% appeared in the second biopsy as normal embryo. Another study from a Gleicher group, 11 aneuploid embryos, 37 biopsies, took several biopsies from the same embryo and also sent them to different laboratories so they could look at the inter-laboratory and inter-embryo congruity. And as you can see here again, same figures, 36% of the embryo that in the first biopsy were abnormal, in the second biopsy appeared normal. So the mosaicism rate is not 1 and 2%, but it's actually 30, and even you will see later that even more. They also show that the inter-embryo analysis, 50% differed between biopsy size. So there was a very high inter-embryo incongruity. So as I showed you here, from this result, a PGS nowadays, taking biopsy from the trophic ectoderm is not precise. And how we can improve this precision? So this is another study by Gleicher and a mathematician from Rockefeller. They looked and tried to calculate how many cells you have to take from the trophic ectoderm so that the result will reflect all the trophic ectoderm in the blastocyst. So they use this equation. As you can see, in order to get a precise result, you need to take a biopsy of 27 trophic ectoderm cells that would reflect all the blastocysts. 27, is it too much, too less? So again, a study from this group of Scott showing that if you have a lot of DNA in your biopsy, meaning that if you have more trophoblasts in the biopsy, and more DNA, so ongoing implantation, ongoing pregnancy rate actually decreases. Same result as they showed with day 3 biopsies. So you cannot take too many trophic ectoderm, because if you take too many trophic ectoderm in order to increase precision, you will impair implantation rate. What about accuracy? So this is the two known studies, one by Gleicher, one by Greco, showing that when you're transferring mosaic embryo, it might result in a normal newborn, so false positive. Another study from Monet, reprogenetics, very large data. They transfer a embryo with different type and percent of mosaicism. And as you can see here, no matter what was the type of mosaicism or the frequency, live birth rate was very nicely about 40%. So transferring mosaic embryo might result in 40% live birth rate, false positive. How many embryos were born after transferring mosaic embryo? So Patrizio in 2011 made this estimation and showed actually demonstrated actually in 2018 probably more than 200 newborns, normal newborns, were born after transferring of mosaic embryo. So there are many newborns now, normal, euploid, that were born after transferring of mosaic embryo. What about false negative? So again, another study for NYU. They looked at patients that conceived after a transfer of euploid embryo, blastocyst, and then miscarriage. And they were amazed. Why did they miscarriage? Transferring a euploid blastocyst should result in high live birth rate with very low miscarriage rate. So they went back into the biopsy DNA, the previous one, the original one, and took used another platform, NGS, on the same DNA that was used in the first biopsy. And as you can see here, first platform showed euploid embryo, second platform, 30% of this embryo that were miscarriage were mosaic, and 5% more were triploid. So there is also a false negative. Actually, the false negative rate is very low. It's not 30% like the false positive, it's about 1-2%. So I showed you that actually PGT-A, PGS nowadays is not accurate and not precise. Meaning that if, let's say that you are suffering from diabetes and they can give you some applicator that you're inserting to your ear, which give you your plasma glucose levels, and according to this level, you should inject the amount of insulin. So I believe that nobody will percuss such an applicator with these figures of accuracy and precision like I showed you in the PGT-A, because you probably will suffer from hyperglycemic coma or hypoglycemia, because the results will not be accurate. How we can explain this high rate of mosaicism? It's actually biology, simple biology. This is a very elegant study by the group of Magdalena Zernica. They could create a mouse embryo with different percentage of euploid and aneuploid embryo, mosaic embryo, and as you can see, when they transfer an embryo with 100% euploid cell, all the embryo implanted and result in healthy pap. When they implanted embryo with 50% euploid blastomer, so again, all of them implanted and result in viable paps. When the percentage of euploid blastomer were 33%, so only part of this embryo implanted and resulted in viable paps, and only when all the blastomers were aneuploid, there was no implantation. They also looked at this embryo by a time-lapse microscopy after staining this cell to euploid and aneuploid, so they could differentiate between the euploid and aneuploid cell. And when they looked at them using the time-lapse, they showed that the abnormal cell within the inner cell mass, this one, were significantly more likely to undergo apoptosis, self-correction, than those with the trough in the trough ectoderm. So meaning that if you're taking a biopsy from the trough ectoderm with the aneuploid cell that didn't go apoptosis, the result will be aneuploid or mosaic embryo, while in the inner cell mass already corrected himself, it is normal. So you're actually discarding a lot of embryos that's supposed to be abnormal according to the trough ectoderm biopsy, while the inner cell mass is normal. So the embryo, the mice embryo, has the ability to self-correct themselves downstream. What about human embryos? So I will show now a film of an egg, and using the time lapse, you can see here that already during the first division, it expelled one cell outside the zona pellucida. You can see here the embryo that developed from the same fertilized egg. These two embryos develop through the blastocyst cell that you can see here. We splitted these two embryos and sent them to two genetic tests. One is haplotyping them, and as you can see here in the lower part of the slides, they are actually identical twins. See these two very nice blastocysts. When we used NGS on this embryo, so the one that was within the zona pellucida was euploid, while the one that was expelled was aneuploid, meaning that actually an embryo can recognize an abnormal cell and expel it, correct himself upon the first division. This is another film of an embryo using time lapse, and you can see here that there is divided very nice embryo. And you will see that while during compaction, the embryo is expelling cells. You will see it in a minute. So when we trace more than 100 films, you can see here the embryo. Look at the arrow. The arrow is expelling cell from the contact, another cell that was expelled, and another one. The embryo has the ability to expel cell during development. And we saw that 60% of the embryo expelled cell during development. And here you can see this zona pellucida with the expelled cell after the blastocyst was etched. And we took this blastocyst and also this expelled cell, and we used NGS, and we saw that this blastocyst was euploid and the expelled cells were aneuploid. Actually, during development, the embryo has the ability to expel abnormal cell. The abnormal cells are abnormal, aneuploid, and the embryo is already euploid. This is actually an observation that is against non-invasive PGT-A, because in non-invasive PGT-A, you are examining the medium or this DNA, the DNA from this expelled cell that is abnormal, while the embryo is already normal. So you will examine this DNA, you will say that the embryo is aneuploid, while the blastocyst already corrected itself and it's normal. So let's now, after showing that there is no logic to use PGT-A nowadays using trophectodermal biopsy, let's believe that we'll find the way how to examine the blastocyst or the embryo and taking a biopsy from the inner cell mass somewhere else. And now we have, let's do reset, now we have a test that is 100% accurate, 100% precise. And now we want to apply it into clinical practice. And before applying it, we need an RCT. So this is what Braude wrote about the expected RCT in his RBM, in his opinion, published in RBM Online in 2018. Despite public announcement that registered, randomized, properly structured, non-commercial trials are in progress, no taker so far of this appropriate way, and this is actually understandable because turkeys do not vote for Christmas. We could understand all this statement already in 2015, and this is why we create this theoretical RCT. We call it the pre-implantation screening, the required RCT that has not yet been carried out, and I believe that even nowadays it was not carried out. So we created this hypothetical RCT looking at the primary outcome for cumulative live birth rate plus TOAD, and we looked at three groups: patients that underwent screened PGS blastocyst embryo transfer, non-screened blastocyst, and also patients that underwent a cleavage stage day 3 embryo transfer. We started with 100 good quality embryos, and then in order to fulfill this RCT, we need several figures: the blastulation rate, aneuploidy rate, and implantation rate. So we went back to the literature, and you can see this Cochrane review looking at blastulation rate. So we know that the blastulation is about 50%, 47%. And when applying this model, so we can see here that now we still have 100 cleaved embryos, but in these two arms we have 47 blastocysts. Now, what about euploidy rate? So we can see in this very large number of embryo young patients that underwent PGS from epigenetics, only 43% were not euploid. Same result actually like the STAR study that I will show you, that I will discuss later. So if we apply this euploidy rate to this model, so we started with 100 day 3 embryo, now we have 20 euploid blastocysts, 47 non-tested blastocysts, 100 cleaved cell embryo. Now we should introduce also the ongoing pregnancy rate. This is the DADU meta-analysis that I showed you at the beginning. 65% for euploid, 47% for non-tested. It's a bit high because, as you can see in the STAR study, the ongoing pregnancy rate of euploid blastocyst study is about 50%, not 65%. Not about day 3, it's about 30%, but it's range between 21 and 50%. This is Scott study. So if we will apply this number of implantation rate to the model, you can see here that the best result you can achieve if you are transferring day 3 embryo. The second best is transferring blastocyst non-tested, and the worst result, cumulative live birth rate fresh post-TOAD, is when you are transferring an euploid blastocyst. It's logical because PGT-A does not correct embryo. It's only selecting the euploid one, and the one that supposed to be aneuploid and are already correct themselves are also discarded. So what do we know about real-world practice? This is a study from Cornell. they looked at the day 5 embryo transfer with and without a PGT-A, and they stratified the data according to patient age, below and above 37. So below 37, as you can see here, live birth weight with and without PGT-A were the same, and miscarriage is also the same. So actually, as we suppose at the beginning, PGT-A should be targeted to elderly patient. In young patient, there is no benefit of using PGT-A. And in elderly patient, they showed that there is significantly higher live birth rate using PGT-A on per transfer compared to non-tested blastocysts. But this is not what we are looking for. We're looking about live birth per started cycle. And they looked at this data too. In Cornell, 191 couples started PGT-A with the age above 37. Of them, 26 had no blastocyst. In our group, I believe that this number will be 70 or 80, but Cornell has also this patient selection also for elderly patients. So 26 couples had no blastocyst. The rest underwent PGT-A. 105 had no euploid blastocyst for transfer. So actually, of these 191 couples, only 60 had the transfer of blastocyst or euploid blastocyst. Of them, 41 conceived. So if we're looking for pregnancy or live birth rate per started cycle, it should be 45 per 191 couples that started the treatment. So it's 21%. But what you can find in this IVF Center website, you will see the 68%, which is the live birth per transfer. And this is actually the marketing number. And the real number is this. That's what you should tell your patient, and not this 68%. And now we're going back to the STAR study. This is a study that all of us were waiting for. This is the real RCTs. They included patient 25 to 40. Why not 37 to 45? Never mind. And the patient had an average of 7.4 blastocysts, meaning this is not, it's a huge, the best of the best of our patient, the creme de la creme, because I'm not seeing patient with 7.4 blastocysts on a routine, in our routine practice, or maybe 1 in 2 weeks, no more. So this were the patient, the creme de la creme, young patient that underwent this PGT-A. And as you can see here, when they looked at PGT-A versus control, PGT-A, using PGT-A has no benefits, same live ongoing pregnancy rate. So they start to manipulate the data above and below 37, 35. Why not 37? I don't know, but let's say 35. And here they showed that below 35, no difference, and within 35 to 40, there was significantly higher ongoing pregnancy, meaning that PGT-A should be targeted to patients between the age of 35 to 40. I want you to pay attention to miscarriage rate in this study, no matter in which age they looked. Miscarriage rate was similar in all the group with and without PGT-A. So all these proponents of PGT-A that always say that PGT-A reduces miscarriage rate, you can see here that it doesn't. So PGT-A does not reduce miscarriage rate in the real world practice. Now let's look at the data again. This is the flow chart. If you're looking at the flow chart very carefully, digging in, you can see that they excluded patients with they didn't achieve 2 blastocysts. They excluded patients with no available euploid blastocysts for transfer, and they excluded patients that had a toe failure. Why? We should include all the patients that started the study. So if we will go back and including this in the denominator, all these patients were excluded. So you can see here that instead of 313 and 274 analyzed patients, we should have 400 and 405. And analyzing the data again per started cycle, this is the original result. You can see here that for all the patients, the corrected analysis with the real denominator, no difference. If you're looking at patient 35 to 40, again, if you're looking at the corrected denominator, again, there is no difference. So even the STAR study showed actually that there is no benefit of using PGT-A in any age if you are looking at a clinical pregnancy rate or live birth rate or ongoing pregnancy rate per started cycle. Here's another claim, this is the last claim that the PGT-A proponent always saying is that using PGT-A decrease the time to pregnancy. So let's go and see. You're doing we're doing IVF cycle in non-PGS, and we know that in PGT-A we have 65%, and I showed that it's lower, but nevertheless 65% ongoing implantation rate, and 47 in the non-tested blastocysts according to the DO. After the first cycle in the PGT-S, there is no transfer because we are taking biopsy and cryopreserving all the embryo, and here we have 47 pregnancies. So starting in the first months, there is more pregnancies in the non-PGS group. And then another cycle, transferring euploid frozen told blastocysts, 65%, and here another 47 million received, so 72%. And actually, only after the third month or third cycle, the numbers are equivalent. And the time to pregnancy is shorter using a cycle without PGT-A compared to a cycle with PGT-A. So I believe that I convinced you that nowadays PGT-A should not be used as a routine and only in clinical trials. Thank you for your attention.
Hello, I'm Norbert Gleiche, MD, and I'm the last